I want to show you a problem that makes kind of an interesting point about a couple of interesting points about how to do these proofs. We want to show that the sum from n equals 1 to infinity of the natural log of n over n to the 1.1 converges. By the way, I've put here show because that's the way the problem is written in my notes, but I'm going to cross this out and say prove. I know that some people sort of get freaked out when they say, oh my God, I have to prove something. But it's the way I see it is we don't want to we don't really want to euphemize the problem. The person should they should drink their math straight from the tap, the way I see it. So we're not going to show, we're going to prove. Uh, Perhaps lesser math classes can show things, we prove them. So anyway, um, the it's not clear exactly how you would do this. It turns out you can do this by either the LCT or the DCT, but it's a little easier to do by the DCT if you know one fact. The fact that you have to know is this, is that um, the fact that you want to know is that ln of n is less than n to the a for any a greater than 0. In other words, it doesn't matter what the exponent is. I can choose any exponent, and this is true. I need one little term, though, to say this, which is eventually. I'll show you why this is, but the point is that if I look at the graph of ln n, and I look at the graph of n to the a, so this is, let's say the purple is n to the a, and the green is ln of n. It starts out that it looks like ln n is going pretty strong. N to the a, like let's suppose that I take a as 0.0001 or something like that, some really small number. It starts out that like n to the 0.001 is barely growing at all. But the point of this is that eventually, as I carry this out all the way here, eventually n to the a is going to somehow overtake ln n, and it's going to stay there. It's going to stay as the greater function. So ln n is just slower growing than any power function. It may not be the slowest, it may not be the smallest function for a while. I mean, it could take up to 100 million before this becomes true, before n to the 0.0001 overtakes ln of n. I don't know what the number is. It could be very large, but eventually it will overtake it. And of course, we don't really care what happened for the first 100 million terms because that's just a finite number. We only care what happens from some number like 100 million up to infinity. That's why I say eventually. It's not the case that this is true for every possible n, but eventually it will become true and it will stay true all the way out to infinity once it happens. So I'll show you in a minute why that's true, but for now let's just take it on faith so I can show you how to use this fact in the proof. So let's say that we're going to use the DCT. Now what I want to observe is I want to use this fact that ln of n is less than n to the a, but I'm going to use a very specific, for choice of a, I'm going to choose a to be 0.05, and you'll see why in a minute. There are a lot of different values of a I could have chosen, but I'm going to choose that. So this is eventually going to be true. I don't care how eventually, as long as it's true. So if that's the case, then I can say that ln of n over n to the 1.1 is less than n to the 0.05 over n to the 1.1. This is, of course, by properties of exponents, is equal to 1 over n to the 1.05. I can just subtract that 0.05 from the 1.1 and rewrite it this way. And of course, here we have our friend p term for a series. So what that means is that I can say that the sum, oh, and by the way, of course, these are positive terms. This is going to be greater than or equal to 0 because, of course, the natural log of 1 is 0 and all other terms beyond 1 are positive. I have the correct inequality. I can now say that the sum of 1 over n to the 1.05 converges. You know what to say. It's a p-series with p equals 1.05, which is greater than 1. Therefore, the sum of ln n over n to the 1.1 also converges. Okay, so all we really did here is we introduced this principle that the natural log function grows slower than any power function, and therefore it's always correct to say that ln n is eventually less than n to the a, as long as I choose a positive exponent a. It doesn't matter how small. Notice that I chose a in this case so that it was small enough that when I subtracted it from 1.1, I was still going to get an exponent that was greater than 1. That was what was necessary to ensure convergence. So let's go over a couple of points. Why not just say ln of n over n to the 1.1 is less than 1 over n to the 1.1? The answer is because it's not true. I can't do that. It's certainly true that this is a convergent, that this is the term of a convergent series, but ln n is ln n is still greater than 1, so this inequality wouldn't have worked. Next point is, why is it true that ln n is less than n to the a for any positive a? Way to look at it is, sorry, um, way to look at it is, let's suppose that I calculate the ratio. Well, let me just write out the ratio. Ln n over n to the a. If ln n is less than n to the a, then we would expect this ratio to be less than 1, right? And of course, we're only concerned about what happens after the first 100 billion terms or something like that. So let me calculate the limit as n approaches infinity of this ratio. So in other words, we start out like this. These are these two functions that are somehow competing with each other, and I claim they cross each other eventually. What I want to do is out here after 100 billion, well, I'll write 100 million because I don't have enough room for that many zeros. After 100 billion, what I want to do is I want to know, not at the beginning what this ratio is, but after 100 billion terms, what is this ratio going to be? I can calculate it like this by the L'Hopital's rule. I'll just write the h there. This is equal to the limit as n approaches infinity, and I can use L'Hopital's rule because this is infinity over infinity. This is going to be 1 over n as the derivative of ln n, and then a n to the a minus 1. When I simplify this, limit as n approaches infinity, I get 1 over a times n to the a. And since a is a positive number and n to the a grows to infinity, this is just going to be 0. So focus now back on this expression. What I'm saying is that if I let n be large enough, the ratio of ln n to n to the a is 0. In other words, ln n is so much smaller than n to the a that their ratio is eventually just going to be 0. That sort of demonstrates that in the long run, ln n is going to be much smaller than n to the a. And notice the only thing that this calculation that I did depended on was that a was a positive number. So that's how we know that ln n is much smaller than a. But just going back to this, the point was really up to here to show how to do this problem.